Hello and welcome to lesson 1.1 and 1.2, rates of change and the slope of the curve and the difference quotient. So first of all, we're going to remind ourselves what average rate of change is compared to instantaneous rate of change. So I'm going to draw a sketch of a function here. Let's say this is our function f of x. Well, if we want to find the average rate of change between two values, let's call them a and another one value b, we need to find f at a and f at b. And then what we're doing is we're calculating. I'm going to use my ruler here as best as I can. And right here we're calculating the slope to find the average rate of change by taking f at b minus f at a, and we're dividing by b minus a. And that's going to give us our average rate of change. Well, our instantaneous rate of change, how is that different? Well, instead of drawing a secant line for a function, instantaneous rate of change occurs on a function at a specific point. So let's just call that point A. And what we do is we draw a tangent line, which kind of like bounces off the function at that spot as best as we can, and we measure its slope. Well, in order to do this, what we choose is we choose something that's really close to the value A, and we call that A plus H. Then we draw a tangent line, sorry, my apologies, a secant line between A and A plus H, which approximates our tangent line as best as we can. So then we're calculating the slope in this case using f at a plus h minus f at a all over h. And as you can see, this green line turns out to be an approximation of our function and our slope at that value. So it's an approximation, it's an estimate. And this only works for h values that are close to 0. If we choose the value 0 as our value of h, then we get a function as 0 divided by 0, which we have not been able to calculate yet or figure out. So the instantaneous rate of change can only be estimated based on the smallest possible interval that we can choose. And again, I stress the fact that it's an estimate. Also notice graphically that the instantaneous rates of change accuracy depends on the sketch and depends on your approximation of the instantaneous rate of change. So one suggestion is to calculate this instantaneous rate of change instead of using what we saw in advanced functions to simplify the algebraic expression given by the difference quotient. This has always been a suggested option that we can use in order to see if it will work out. So we'll try that a little later and see if it will work out and give us a better solution that's not an estimate. Okay, so let's say we're given this function off to the side and the right. We don't need to actually calculate the function's equation, but we want to calculate the average rate of change between the value of x equal to -3 and x equal to 3. So first off, I'm going to locate where -3 is and 3 is. Locate those points on the function, and then draw my secant line there. Well, if we want to calculate the slope, I need f at -3. So f at -3 turns out to be -12, and f at 3 turns out to be 0. So you take these y values, you subtract them from each other. You take the x values in the same order and subtract them from each other. And you calculate this. So negative 12 over negative 6 gives you positive 2. So the average rate of change between these two is positive 2. Again, to calculate the instantaneous rate of change, you find your slope at the value of 1. So first locate where x is 1 and draw your point. Take your ruler and then try to draw your tangent line as best as you can. And again, your tangent line is going to be slightly different from everybody else's tangent line. So your slope will be slightly different from somebody else's. Again, take 2 points on your line and then try to find the slope between those 2 points. So I'm going to use that point that I generated, 1 and negative 12. And I'm going to take this point right here, 3 and negative 5. This time I'm going to calculate my slope using a rate triangle. So here my rate, or my run, is 2 units. My rise is 2, 4, 6, 7 units. So in this case, my instantaneous rate of change is approximately 7 over 2, or, if I wish, 3.5. But again, this value is an estimate and is an approximate number based on your drawing of your slope. Okay, so let's try to do something that we did in advanced functions. So in advanced functions, you want to determine the instantaneous rate of change at x equals 3 for the function f of x equals x squared plus 2x. And here we're going to simplify the difference quotient. But let's see how we would have done this if we used advanced functions. So I'm going to write over to the side here, advanced functions method. So in advanced functions, we calculated f at 3. We added a value that was really close to 0. So how about like something like 0.001? We subtract f at 3, and we divide by 0.001. So I'm going to grab my calculator. I'm going to work this out using my calculator. So f at 3.001 gives me 15.008001. F at 3, that would just give me 15. I'm going to subtract that, divide by 0.001. Oops. So using my calculator, I get a value 8.001, which is approximately the value of 8. So that's what I would say might be my instantaneous rate of change. Well, let's try doing this if we can just simplify the difference quotient this time. So this is our difference quotient. If you want, you can substitute a as 3 here or later. And again, h as a value close to 0. You probably want to put that in later. So we're going to substitute those later. Here we're just going to simplify the difference quotient. So here we're going to take a plus h squared plus 2 times a plus h. That's because we're substituting a plus h in for our function. We're going to subtract f at a, which is just a squared plus 2a. And we're going to divide this all by h. So a plus h squared is a squared plus 2ah plus h squared plus, now we expand the 2a and the 2h, So 2a plus 2h minus the a squared plus the 2a all over h. Okay, so here I notice a squared cancels with minus a squared, 2a cancels with, oops, forgot to distribute. That's a negative 2a. So the 2a will cancel with a negative 2a. That leaves me with 2ah plus h squared plus 2h all over h. Well, I can factor out an h from my numerator. And cancel it with my denominator. So this gives me a value of 2a plus h plus 2. So that means if I wish to calculate this instantaneous rate of change, I'm looking at 2 times the value of 3 plus 0.001 plus 2, which again gives me a value of 8.001, or approximately 8. The only thing is, what if h was 0 here? If h was 0, that would give us our exact value of 8. Well, the only reason is that we can't substitute h equal to 0 here is because of this step right here. H cannot equal 0 based on this function, because if it was 0, it would be something undefined and therefore would cause a problem. But what if we could make that value of h equal to 0? So that leads us into our next lesson, 1.3, where we will see where we can, or what we'll do is we'll find some way of creating something that will allow us to get infinitesimally close to 0 and actually substitute it in.